Well, hi everyone. I hope you're having a great conference. I'm glad to be here in this session. So I'm going to talk about some work on the habitable zone, which I hope by now you've heard about. And this is work I've done with Ravi, Natasha, Sunny, and Jim Casting. So to start with, what do we mean by a habitable zone? We mean really a liquid water habitable zone. This is important because as astrobiologists we like to be imaginative and we don't want to say that the habitable zone is the only place that could possibly ever be habitable. But this is an observational tool that helps us constrain exoplanet observations. It's based on the orbital distance of a star, the orbital distance of a planet from a star. It's the region where you could sustain liquid water on the surface. Well, what do you really need for that? You need a rocky planet. This doesn't really apply to gas giants. You need an atmosphere with N2, water vapor, and CO2. This is at least the assumptions that go into our models. You can do this with some other greenhouse gases, and there's plenty of papers that do that. But for calculating just the essential outer and inner edge of the habitable zone, we're really interested in water vapor, CO2 as greenhouse gases, and nitrogen to buffer the atmosphere, add some pressure. You also need some method for recycling volatiles. Plate tectonics is a really good way of doing this. We don't really have any other great examples of other ways of recycling volatiles on Earth, but there's some theoretical ideas out there, stagnant lid or something like that. But you need to be able to recycle the volatiles. So this plot, I hope many of you have seen. I will go through it very briefly, though. This is the habitable zone as drawn by Sunny. We have the effective temperature of the star here, or you can just think of this as stellar type, so F, G, K, M dwarfs down here. And this is the effective stellar flux. You could also think of this in terms of distance if you want. So this is closer to the star. This is further away from the star. Earth is right here. We're situated in this nice habitable region where we can have liquid water on the surface, thankfully. But if Earth were to be pushed a little further in toward the sun, you would start to increase the rate of evaporation of oceans, and you would actually start to lose your water vapor. What would probably first happen is a moist greenhouse where the water actually gets photolized out of the top of the stratosphere. But if you push further in, or if conditions are slightly different, you may even enter a runaway greenhouse where you lose the oceans altogether. Very rapidly. So the inner edge I'm not going to focus much on today. You might hear about that later in the session, though. The outer edge of the habitable zone is where we're concerned for this problem. The outer edge is defined by the maximum amount of warming you can get out of CO2. So if you pull a planet away from the sun, and I'm going to show you on the next slide why this is, but we expect that a planet like Earth that's tectonically active would build up carbon dioxide in its atmosphere as you move away from the sun as it gets colder. The threshold then where it says maximum greenhouse, that's the point at which the warming you get from the greenhouse effect of CO2 is actually outweighed by the cooling that you get from Rayleigh scattering because you have a very dense CO2 atmosphere. So this defines the outer edge of the habitable zone. Beyond that, your planet is basically an ice ball. So what's going on with this outer edge of the habitable zone? Why do I say that you're going to build up CO2? What's going on is it's the long-term carbon cycle, the carbonate silicate cycle we refer to it as. It starts with volcanoes. Volcanoes put CO2 in the atmosphere. The CO2 stays in the atmosphere where it's a greenhouse gas, but you've got water on the planet. You have a hydrological cycle. So some of the CO2 is going to get dissolved in rainwater where it rains out onto land here. When carbonic acid dissolved in rainwater hits calcium silicate rocks, you get weathering, which breaks down into ions that will then run off through rivers into the ocean, where they then saturate the ocean with these ions. If you have life on your planet, life might make shells and things out of these. If you don't have life, that's okay. This process still works. You just saturate your ocean until precipitation occurs anyway. And so then you've got these calcium carbonates on the ocean floor, which then subduct, and metamorphism changes this into CaSiO3 and releases the CO2, which then goes back into volcanoes. So this is a carbon cycle. It's not going to help us with contemporary climate change. It operates on a 500,000 year time scale or so. But this weathering step is temperature dependent. And so as the planet cools, as you move Earth away from the sun in a thought experiment, you're slowing down the rate of weathering, which means you're going to increase the amount of CO2 in the atmosphere. And this is what gives us the outer edge of the habitable zone. Well, what was pointed out, and we didn't actually realize this was pointed out by Tajika, and also Kristen Minot pointed this out in 2015. The weathering process is not just temperature dependent, it's also dependent on how much CO2 you have. And I mean, this actually seems kind of obvious in retrospect. If you have more CO2, you're going to you have more weathering, and you're going to end up with an overall different concentration of CO2 in the atmosphere than you would otherwise have. So this is important because this actually gives us some very different behaviors that are transient, some time-dependent climate states that we didn't get otherwise when we only considered the temperature dependence, not the CO2 dependence. So this is what we call, my title has the phrase limit cycle. And so this is a climate limit cycle, which means you're alternating between a glacial state and a warm state driven by these oscillations in CO2. So what I'm doing, these are calculations with a one-dimensional energy balance climate model. I start planet. This is a planet around a G star. I'm looking at like an early Earth case where the solar constant's about 70% and in a tenth of the volcanic outgassing rate as today. And I'll explain why I chose that in a minute. So imagine that you start with a cold planet that's an ice ball and completely frozen, and with an active carbonate silicate cycle. So what happens is you're a frozen planet, so you've got volcanoes outgassing into the atmosphere, adding greenhouse warming. So this green line shows CO2. Here's the axis for CO2 partial pressure. Black line is temperature. So as we march forward in time, you're building up CO2 slowly from volcanoes. Now the surface is frozen, so you're not weathering any of it down. You're just building CO2 in the atmosphere. So we continue building CO2 in the atmosphere until you reach this critical point where you've got enough warming that your ice melts. You deglaciate the whole planet, and you very rapidly warm. So now you're warm, you're above freezing, you're a habitable planet in the sense of being able to have liquid water on its surface. But what happens? Now weathering turns on. You start drawing down all the CO2 from the atmosphere, and we get this sawtooth. CO2 goes down because weathering turns on. Well, now you've lost your greenhouse effect, so temperature goes down as well. You plummet back into a glacial state. And so this is what we call a limit cycle, is long periods of glaciation followed by punctuated periods of warmth repeated over time. This limit cycle phenomenon doesn't behave the same around all stellar spectral types. It's actually a function of stellar type. So here's what the plot I just showed you, exactly the same. That's around a G star. So here I've kept the parameters the same, still 70% of solar constant, same volcanic outgassing rate. We're just around an F star now, so a hotter star, but it's not just hotter. It actually puts out more energy in the blue end of the spectrum and less energy in the red end of the spectrum. So what that does is you get enhanced ice albedo feedback. This has been discussed by, I think, Bob Haverly and Oumuamua Shields and others that you would expect this. So you get enhanced ice albedo feedback around an F dwarf stars. And so that actually just increases the frequency, the timing of these events. So you build up CO2 here, you warm, but notice how sharp this peak is. You have a very, very narrow range of time when your planet is warm. Most of the time you're in this cold phase where you're just building up CO2 in the atmosphere, but not deglaciating. So this suggests that if a planet is caught in this limit cycle, perhaps the G-type stars have a slightly more likelihood for sustaining longer periods of warmth than the F dwarfs. Now, I've mentioned volcanic outgassing rate a couple of times. The volcanic outgassing rate, as you may imagine, is a very critical parameter for this because that determines how quickly do you build up CO2 in your atmosphere. And so I've shown that here, right here. This is the volcanic outgassing rate where 10 to the 0, this is just based on, it's scaled to present-day Earth. The other important factor to think about, though, is how much CO2 should be dissolved or sequestered in soil. Now, it's a tricky question, and I'd love to talk to you more about this later. I don't want to get bogged down in the details. But on Earth today, CO2 sequestration is very much driven by life. And if we had a planet that was in limit cycles, you may think that your soil's not going to be fully inhabited by microbes. You may reach a very different equilibrium soil CO2 concentration. And so what we've shown here is this is the range of parameter space where CO2 partial pressure versus outgassing rate. In this shaded region, you would expect limit cycles, whereas in this gray region, you would not expect limit cycles. This is just illustrated for a G star around for an early Earth case. Really, the point of this plot is these two things are not really well constrained for exoplanets. We got a good idea of these values for Earth today, but they're not easily constrained with observations, but I think we need to think more about what would we expect outgassing and soil CO2 to be on exoplanets. So when we do this, here's the new version of the habitable zone that you get. It's a function of the volcanic outgassing rate, as I just mentioned. So we've drawn a couple lines here. This line is if the volcanic outgassing rate on the planet is 1/10 of Earth today, and this is if it's half of today. If it's equal to Earth today, then this line is out here and the planet doesn't have limit cycles at all. So again, it's definitely a function of volcanic outgassing rate. So you notice here around F dwarfs, this habitable region, this blue region, there's no limit cycles then. In this region here, there are limit cycles. So for F dwarfs, this range of stable climates is very small compared to G dwarfs, whereas K and M dwarfs actually remain stable without limit cycles at all because they have reduced ice albedo feedback. So the last thing I want to mention is we also looked at applying this not just to the outer edge of the habitable zone in general, but specifically to the problem of early Mars. Could the fluvial features on early Mars be telling us that Mars was caught in this limit cycle early on in its history? And this just is a slightly different way of plotting it. Average surface temperature here, CO2 partial pressure. And what we're showing here is this red line gets above this weathering curve, which means you're going to cycle. Sorry, this plot's a little confusing, but the basic message is if you have, in these calculations, if you have an 80% CO2 atmosphere with 20% hydrogen, you get cycling, whereas if we have only 5% hydrogen, we don't get cycling. However, Robin Wordsworth recently did some calculations where he showed that in a mixture of CO2 and H2, you actually get collision-induced warming from the hydrogen that actually is much more efficient than this. So we're actually redoing some of these calculations now, and we're pretty sure that you're going to be able to show that you can get cycling on Mars with much less hydrogen than we've required. And so I'm at the end of my time. I'll just stop here and take some questions.
If you're able, please go up to the microphone to ask your questions.
Hi, Jacob. Colin Goldblatt, University of Victoria. I'd like to add to your introduction a little bit, which is the CO2 dependence of weathering was proposed by a paper by Berner in the early 80s. And then there were limit cycles in the earth science literature, especially from Tajika's group, in some lovely papers in the late 90s and early 2000s. And I know that Jim didn't realize that, so I'll blame your PhD advisor for this one.
Well, we do cite those in our paper.
Okay.
But
great.
yeah, no, that's a very good point, that actually before people thought about limit cycles for exoplanets, it was thinking about, does this explain some features of early Earth? And I think you even are on a paper where you look at the Snowball Earth episodes, if I'm correct. And
we've got a paper a few years ago.
So this may have occurred on Earth as well for other reasons.
Yeah. A more substantive question is, why does it matter? If you have some warm periods, let's just thrive then and set down spores which can last for millions of years between those limit cycles, and we're just episodically habitable.
Yeah, I'm glad you asked that question. And oh, my slide disappeared. That's okay. I had a statement that said Earth-like planets with complex life may be less prevalent than those with simple or no life. And I put a question mark there, and I was actually thinking about you when I put that question mark there. Because you're right. What does this mean if you have 80 million years of glaciation followed by 10 million years of warmth? We wouldn't like that. Our type of complex life would not survive. I would not make the strong statement that all potential life in the universe cannot survive this. So this is a question to be had. I think I have an easier time imagining microbial life surviving that type of transition than something resembling complex animal life. But we should have this conversation.
Thanks, Jacob.
We have time for one quick question.
In the carbonate silicate cycle, do you have any idea how efficient the pulling up of that CO2 during volcanism is? Is it 90% goes back up into the atmosphere and 10% keeps on going down, or do you have any idea about the relative percentages there?
I don't know that number. Ravi or Colin, do you guys know that?
That's the volcanic outgassing number.
It's
quite poorly constrained. It's one of those numbers that we would really love to know relative to carbon.
But for the cycle that you're invoking here, you're assuming 100%.
That's right. We just prescribe a volcanic outgassing rate. That's how much.
And when you set the solar constant equal to 0.7, you're assuming that you have 30% land on the ocean, on the Earth, rather than the almost 0% land covering that most Earth scientists who study continental growth will tell you?
We had Boy, I can't remember what land distribution we did. Was it? I think we did aquaplanets actually.
We'll have to cut it off there, and you guys
Okay,
will have
we can
to
talk more.
after that.
All right, let's give him another round of applause.